Alright guys, so I wanted to talk about some simple machines, ideas, key ideas, and go through a problem example as well. So first thing we want to understand about machines is that the whole purpose of a simple machine is to make work easier. And it really does that in one of two ways. Either it does that by changing the direction of a force, so like a lever or something like that, you can push down and lift an object up, or by increasing the amount of output force you get for a given input force. So another way of saying that is you're able to exert one force and get more force out of the machine. Okay, so that's how machines make work easier. But there's always a trade-off. So you're never going to get more work out of a machine than you put in. That's impossible. You can't get more energy out of something than you put into it. All right. So what we can think about is, ideally, if there were no friction, if there were no air resistance, then the amount of energy or the amount of work that you put into the machine would be the amount that you get out. So that's the first concept, is the idea that the work you put in an ideal situation is equal to the work you get out from the machine. Okay. Now we already know that work is F times D times cosine of theta. But when we're talking about machines specifically, we can actually reduce that and make it even simpler and just do force times distance. And the reason for that is because the machine is always going to exert a force in the direction that the object is moving. All right, so we don't have to worry about that whole cosine part of it. Just force times distance is good enough. All right, so if we know that this is work, and we know that work in equals work out, then that means the force you put in times the distance over which you exert that force has to be equal to the force that you get out from the machine times the distance that the machine moves whatever it's trying to move. So this is the work you put in, and this is the work you get out. That's the ideal idea. Okay. Another key concept is mechanical advantage. And mechanical advantage is basically a way of describing how strong the machine is compared to the user. All right, so if the machine can exert 3 times more force than the person who's using the machine, then it has a mechanical advantage of 3. It's just a ratio that tells us how strong the machine is in terms of force compared to the person who's exerting the force on the machine, like the pulley or lever or whatever it is. Okay, so there's 2 ways to describe mechanical advantage. There's the ideal mechanical advantage. Now that would be if there was, again, no friction or anything like that. And the way we calculate ideal mechanical advantage is take the input distance, that's d in, and divide by the output distance, that's d out. So how much string did you have to pull, or how far did you have to push down on the lever or whatever, that's the input distance. And then the output distance is whatever the machine does to move the object. How far did it move? Okay, so that's how we calculate the ideal mechanical advantage. All right, when we talk about actual mechanical advantage, because no machine is perfect, the actual mechanical advantage is the force you get out from the machine divided by the force you put in. All right, so if you get 4 times as much force out as you put in, then the mechanical advantage will be 4. Okay, so I want to go through this example problem here, and we'll work through it together. All right, so it says a pulley system requires the user to pull a rope with 50 newtons of force and pull 1 meter of rope in order to lift an object 0.4 meters. Question A says, what is the output force of the machine? And question B, what is the machine's ideal mechanical advantage? All right, so we're going to answer these 2 questions. But before we do that, it's very, very important. If we're going to use these equations, we need to make sure we understand first that whenever we're talking about input, input is whatever the user does. All right, so that's, the person pulling down on the rope in a pulley system, or pushing down on a lever, or pushing an object up an inclined plane or something like that. What the user does is the input. The output is what the machine does. So if you're trying to lift an object using a pulley system, all right, the object being lifted, that would be the output force, and how far it lifts that object would be the output distance. Okay? So in part A, when it says, what is the output force of the machine? To answer that question, let's first write down what we know. We know the user is pulling the rope with 50 newtons of force, so that's the input force. We also know the user pulls 1 meter of rope, so that's the input distance. Okay? We know that the object gets lifted 0.4 meters, so that means the pulley is lifting the object that far. So that's our output distance, and we want to know what's the output force. So we can put a question mark there. Okay. I know that ideally the work that you put in has to equal the work that you get out. So we can say force in times distance in, that's the work you put in, equals force out times distance out. And I'm going to write down what we know. Force in is 50 newtons. Distance in is 1 meter. Force out I don't know, so I'll just write it down again. And distance out is 0.4 meters. So if I want to get force out by itself, I'm going to divide both sides by the 0.4 meters. So that's what I did here. You notice that it cancels out on this side. Over here I have 50 newtons times 1 meter over 0.4 meters. So if I do this, plug it into my calculator, I get an output force of 125 newtons. So think about it. The person only had to pull on the rope with 50 newtons, and they're able to get 125 newtons out of it. All right, so that is the output force. Get more force out than we put in. The way we do it is we trade off with distance. Notice they had to pull more rope, a whole meter of rope, but they were only able to move the object 0.4 meters. So that's the trade-off. Okay. Now in part B it says what's the machine's ideal mechanical advantage. So for that, I'm going to do ideal mechanical advantage, you see it up here, is distance in divided by distance out. The person had to pull 1 meter of rope. The object was only moved 0.4 meters. So if we divide those two, I'll slide this over a little bit here. 1 meter divided by 0.4 meters gives me an ideal mechanical advantage of 2.5. So that means if there were no friction or anything like that, the machine can exert 2.5 times the amount of force that the person does. So this is a good example of working through some of these calculations and also just a review of some key concepts.